We introduced TorchPoint3D, a new open-source framework for training deep networks on 3D point clouds. 3D deep learning is one of the fastest growing fields in computer vision, as seen with a sharp increase in the number of dedicated papers. 3D point clouds have indeed a lot going on for them. Most importantly, they are well suited to describing our 3D world. They can be produced cheaply and reliably with multi-view stereo techniques or very precisely with LiDARs. Moreover, point clouds are at the center of several major prospective industrial applications, the most prominent of which are autonomous driving and digital twin modeling. However, dealing with point clouds presents several challenges, which makes it harder than dealing with images. In particular, their size and their varying density makes naive transfer of the convolutional paradigm that is so successful in 2D not directly applicable to 3D point clouds. As mentioned earlier, deep learning on 3D point clouds have seen a recent gain in popularity over the last few years. New ideas and networks are being proposed constantly, and the state of the art is rapidly improving. This is great news, but also makes it hard to follow and to know exactly which network is best suited for a given application. These issues are exacerbated by the lack of a common framework for 3D deep learning, in the way that torch vision became the standard for deep learning on images. One of the main issues is that it takes a lot of code to add new dataset to a 3D deep learning pipeline. One must write the loading functions, pre-processing step, a new data loader, and so on. As a result, many researchers only evaluate their method on a small number of datasets. This discourages extensive comparisons between methods and creates artificial barriers to entry. Second, there is no standard evaluation protocol to evaluate the performance of networks on different tasks on datasets. This means that it is hard to know which part of the performance comes from a better augmentation strategy or inference scheme, or if a given network is truly better at extracting rich semantic features. Combined with the fact that modern networks are complicated to re-implement, this makes it quite difficult to assess the true values of new ideas. Furthermore, this lack of standardization increases the chance for researchers to make mistakes or create needless inefficiencies. This has the potential of preventing good ideas to reach their full potential. For anyone who has ever tried to implement a KP-Comp or Minkowski engine from scratch, this is no small feat. These high-performing networks rely on complicated implementation to remain efficient or even to perform as intended. This explains why many researchers choose their backbone network by simplicity rather than performance, and thus why .NET++ is still so ubiquitous after 4 years. Finally, research codes are, by nature, not as optimized as productization code needs to be. This means that development teams must often start projects over from scratch, and as we mentioned, this is a hard task that often requires a good understanding of deep learning in general. These issues are what motivated us to create TorchPoint3D, an open-source unifying framework for all deep learning on 3D point clouds. Our goal is to increase the simplicity, reliability, and reproducibility of 3D deep learning research. And we want to reach researchers and developers alike. We propose a re-implementation of many of the top-performing networks and support many academic datasets. Our configuration system makes it easy to create or modify current network architectures. Our re-implementations are written with efficiency in mind and are robust thanks to our extensive testing and the feedback from a growing community. Finally, the framework is 100% open source. We are looking forward to welcome new collaborators, by the way. Our framework is implemented around the concept of tasks. Several are already implemented, such as shape classification, semantic segmentation, object detection, panoptic segmentation, and registration. Each task comes with its own loss function and tried-and-true metrics. We have re-implemented some of the top-performing algorithms published in recent conferences, such as kernel point convolution, Minkowski engine, and so on. In particular, we propose a powerful system of configuration files for network which follows a U-Net-style architecture, with an encoder and a decoder as originally introduced by .NET++ for 3D. These networks can be set up by a simple configuration file expressing the layer widths of the down and up convolutions, as well as the parameters of the subsampling and upsampling steps. We have been able to re-implement most of the previously mentioned networks into this architecture. Note, however, that TorchPoint3D can and do handle architectures that do not conform with this unit scheme. Think of it as a useful and versatile guideline that allows you to quickly try out new design and ideas. We have added support for many of the public academic datasets, including functions allowing you to download and format the datasets directly from TorchPoint3D. Moreover, for datasets that support it, you can directly upload your results on the submission servers as well. It is well known that proper preprocessing and augmentation can make or break the performance of a network. In this spirit, we propose over 40 different transforms, as well as a system of configuration files that allows you to combine them into a pre-transform, which are only called once at the beginning of training, train transforms called at each iterations, and test transforms called only during inference. We have added several tools for visualization. This can be used to illustrate your results with GIFs and animated notebooks. It is also useful to monitor the performance of your network and gain insight on its inner working and help you squash some bugs. Everything in the framework is tied together by a flexible system of configuration files. This allows you to launch an experiment with a single line. Simply specify your task, the general architecture of your network, where to find its configuration file. Finally, pick the dataset. You can change the parameters of your network by simply editing its configuration file. The modularity of TorchPoint3D allows you to add new datasets, models, or tasks with minimal code, and most importantly, without impacting the rest of the framework. Our configuration system is powered by Hydra. Likewise, we have native support for weight and biases, which allows you to neatly organize your experiments online. This can also be used to share your trained models, along with the configuration files and training curves. This promotes total transparency and high reproducibility. In our paper, we present some of the benchmarks that we ran using TorchPoint3D in order to showcase its capacities. First, we have run a re-implementation of 4 of the most prominent networks on the S3DIS and Scanet datasets. We have made sure that all the configuration, augmentation, and evaluations were strictly equal between networks, in order to be able to evaluate their inherent performance. Predictably, the top-performing network were Capicon and Minkowski engine. We also have run our implementation of the VoteNet object detection algorithm. In the original paper, the authors used the PointNet++ backbone. Thanks to the modularity offered by TorchPoint3D, we have scrapped this backbone and tried other architectures. While it appears that PointNet++ was indeed a good choice by the authors of VoteNet, this illustrates how you can use TorchPoint3D to pick and choose the best suited backbone for your task. We also have evaluated the impact of test time inference. This corresponds to running the inference several times over with augmentations and averaging the network's output. We have observed that just running the inference 3 times leads to a significant improvement in terms of performance, as well as a visual improvement of the prediction. Finally, we have run our experiment on point cloud registration tasks using our re-implementation of state-of-the-art methods on the Kitty and 3D match datasets. We have observed that sampling-based estimators, such as Ransack or Teaser, produce very satisfying results, even compared with end-to-end methods. We have many plans for the future of TorchPoint3D, such as adding even more datasets, backbones, and tasks. We also think that domain adaptation and transfer learning are of major interest, in particular for industrial applications, and are looking forward to trying out some of the best ideas out there. Likewise, self, or semi-supervised methods are particularly relevant for 3D data, which are notoriously hard to annotate by hand. And finally, if you want to support this project, do not hesitate to join us and contribute. We are grateful for the community to help us in this project, since all contributors have full-time jobs or PhD positions on top of maintaining this repository. To try out TorchPoint3D, you can simply install it with pip, or you can follow some of our illustrated notebooks on the repository to learn how to use it. We want to thank all the contributors, as well as the scientists which have advised us in this project, notably helping us to re-implement their own network in an efficient manner.